Hi, I'm Elizabeth Lobo. I'm a PhD student at Chalmers. I'll be presenting a programming framework for privacy-preserving queries with accuracy estimations. This is a joint work with Alejandro Russo and Marco Gaguardi from Chalmers and Boston University. We are constantly sharing personal information that might be used by several parties to learn about users' behavior, improve services, and ultimately make some money. All this data analysis can be beneficial for society, but we don't want it to be at the expense of someone's privacy. In particular, we want to avoid people observing the statistics and being able to identify specific individuals in the data. Differential privacy presents a robust way to protect individuals' privacy by adding some calibrated noise to the data analysis before their publication. Its compositional nature has inspired the creation of programming frameworks to implement such analysis or queries. The idea is simple. Use some primitive with known privacy guarantees as building blocks and use composition properties to combine these blocks to create more complex analysis. The noise added to the result of the analysis introduces some errors that data analysts would like to inspect to determine their accuracy. To compute the accuracy of analysis done with differential privacy in a programmatic way, we will need to define a strategy to compose the accuracy estimations of its building blocks as done with the privacy guarantees. Unfortunately, reasoning about accuracy is complex in nature and less compositional than reasoning about privacy. So it doesn't come as a surprise that existing tools for differentially private queries lack or have limited support for reasoning about the accuracy of the results. In this work, we address this limitation by building Dipela, a programming framework for differentially private data analysis, which also supports a compositional form of reasoning about accuracy. Our framework provides theoretical upper bounds on the errors of the analysis using taint analysis to detect statistical independence of the noisy results to improve error estimations. The PELA also allows analysts to reason about the trade-off between privacy and accuracy statically, meaning by not running the query but rather inspecting its structure. To see how the PELA works, let's start by defining what is differential privacy. Let's say we have a query queue that counts the number of employees with salaries above 60K given the database D. A differentially private version of this query will be Q tilde that takes the same database D, executes Q, obtaining the real count, and finally adds the calibrated noise eta to the result. What do we mean by calibrated noise? Intuitively, we want all our noisy queries to mask the membership of any user from the output. Let's say we have a database D1 with Alice, Bob's, and Charles' information, and then we create another database D2 without Bob. A differentially private query should ensure that by looking at its output, one should not be able to know which database was used for its execution. Formally, differential privacy guarantees that obtaining any output X when running Q tilde over the database D1 is almost as likely as obtaining the same answer X when executed over D2. This is achieved by magnifying the noise to be added depending on two factors. The first one considers how sensible the query queue is to a change of a record in the database, and the second one considers how close we want those probabilities to be. This is determined by the parameter epsilon. When a noisy query satisfies this inequality, it is called an epsilon differentially private query. And the parameter epsilon quantifies the privacy loss of the randomized query. As mentioned before, differential privacy is composable. This is, if we have a set of differentially private queries Q1, Q2 to Qn, the composition of these queries will be also differentially private. So what would be the privacy loss of their composition? The simplest compositional property states that they can be calculated as the addition of the privacy losses of its components. In this sense, we can think about epsilon as a privacy budget that one can spend on a given data before compromising the privacy of the data subjects. With this property in mind, Dipela provides basic building blocks that are grouped as transformations, this is operations that manipulate a given table, and aggregations, which are used to extract information from the database. All aggregations take as input the table, the epsilon to be consumed, and construct an epsilon differentially private query returning a noisy response. In Dipela, data analysis composed by transformations and aggregations are represented by the type query value A, indicating that we have a Dipela computation returning a noisy value of type A. Additionally to this primitive, Dipela provides a function called budget that takes as input a computation or noisy query and statically generates an upper bound of how much privacy budget will be required for its execution. This function provides early feedback to data analysts about the privacy budget consumption, allowing them to optimize its usage. The Pela's interpretation for privacy consists on decreasing the privacy budget of a query by deducting the required budget of its components. Now, to understand how the notion of accuracy is internalized in the Pela's primitive, first we need to check its definition. The accuracy of a numerical noisy query bounds how far we can be from the real value. More specifically, it states that with a probability at least 1 minus beta, the distance between the noisy query q tilde and q is less than alpha. We refer to alpha as the error and 1 minus beta as the confidence. To have an intuition of how do we interpret this definition, let's say that after an execution, the noisy query q tilde returns the value v tilde. Then, for a given beta, say 0.1, which gives us a confidence of 90%, we compute the error alpha. Once we have the error, we can conclude that with 90% confidence, the real value v falls in the interval determined by the error. In general, the lower the beta, the higher the confidence and the bigger the interval will be. Dipela provides a function that statically computes the accuracy of a given noisy query. Function accuracy uses the abstraction of the inverse cumulative distribution function, or ICDF, which returns the theoretical error alpha for any given confidence. Primitive accuracy will not execute the query, but rather symbolically interprets all of its components in order to construct the ICDF of the final noisy value, based on the subqueries and how data gets aggregated. All Dipela's aggregations have a way to generate their ICDF since it is derived from the tail bound of the distribution from where the noise is being drawn. Now that our building blocks have a way to compute their accuracy, we need to determine how do we estimate the accuracy of their composition. In particular, we are interested in computing the accuracy of the addition of a set of noisy queries. A common approach consists in adding the errors of all operands. This is known as the union bound. Although it is a straightforward approach, the error of the final result increases linearly with respect to the number of subqueries. So at some point, the bound provided by this approach becomes useless. So, can we do better? The answer is yes. We can use a tighter error bound called Chernoff bound if we can guarantee that the values being added are statistically independent. In Dipela, we detect the independence of noisy values by using taint analysis. To understand how it works, let's check step by step the query total count written in Dipela. In this function, we will add some noisy values and return their addition. So first, we perform an aggregation, in this case a noisy count, over a dataset DS1 using E1 amount of privacy budget. Its result is then stored in the variable v1. Internally, every time we perform an aggregation, the resulting value is encapsulated in the abstract data type value. Value will carry the noisy result together with its ICDF and the tag used by the taint analysis indicating that its noise is freshly sampled. We will call this an untainted tag. Now, we compute another noisy count and we store it in variable v2. Finally, we would like to add v1 and v2 and return this addition. In Dipela, analysts are not allowed to extract the noisy values to directly perform operations between them. Instead, Dipela provides several accuracy-aware operators. In this case, we use operator add, which takes a list of noisy values and returns a noisy value containing their addition, the ICDF of the operation, and a tag indicating if the resulting value is tainted or not. The result of our addition is marked as tainted since its noise is not freshly sampled. Instead, it is inherited from B1's and B2's noise. To determine the ICDF of the addition, the PELA checks if the tags of the values being added are tainted. In our example, T1 and T2 are not tainted. Then we can say that these values are statistically independent, so their ICDF is computed as the minimum between union and Chernoff bound. Later, we will see why we take the minimum between these two. To see what happens when there are tainted tags, let's define a new value b3 as 2 times b1. To do so, we use the scalar operator, which also returns a noisy value. The result of this value must be tagged as tainted since it derives from b1. Now, if we add b1, b2, and b3, the tag of the addition remains tainted, so no changes here, but when computing the ICDF, the PELA will detect that one of the tags is tainted, in this case the tag of b3. This indicates that the values being added are not statistically independent, so the ICDF of the addition is computed using the union bound, which uses the ICDF of the components. Importantly, the ICDF and the tag of a noisy value can be calculated statically, meaning that we don't need to run the query in a database to generate them. So calculating the theoretical error of a query consists on traversing the abstract syntax tree of our code, gathering the information of the ICDF of the subqueries, and composing them accordingly to the provenance tags. To see the difference between union and Chernoff bound, we update our query total count to perform the addition of n noisy counts. In this implementation, we take as input the privacy budget we want to spend on each count and the number of noisy counts we want to perform. Then we create a count for each I in the range 1 to n, and we store their addition in the variable c. This is then returned as the final result. To inspect the error of total count, we can call function accuracy indicating the privacy budget of the counts, the number of counts we want to perform, and the confidence level we want. In this case, we are indicating a 95% confidence. Now, if our operator add wasn't able to detect statistical independence of the components, the error of their addition would be calculated using the union bound. In this case, we can see that this error will increase linearly with the number of noisy counts being added. Instead, if when keeping track of the statistical independence of the noisy counts the combinator add can apply only the Chernoff bound, it will produce a tighter error estimation most of the time. In general, we can see that the Chernoff bound is asymptotically much better when estimating accuracy, but union bound works best with a reduced number of subqueries. For this reason, when the values being added are independent, the PELA returns the minimum between union and Chernoff. Now we have established a programmatic way to reason about the accuracy of our primitive and their composition, so we can finally present all the components of the PELA's API. As mentioned, it provides primitive for transformations and aggregations, but also exposes to function for estimation of budget consumption and accuracy of the analysis. Additionally, it exposes accuracy-aware operators to combine noisy results. To compare the PELA with other tools, in our paper we have implemented several examples from the literature which we can classify into two categories, ping-like queries and range queries. The PELA supports ping-like queries naturally since our privacy primitive follows closely the ones from ping. However, we go a step further by providing the accuracy bounds achieved by the implementations. By implementing range queries, this is, answering a set of linear queries, we compare the PELA's accuracy estimations with the error guarantees provided by the Apex tool and the matrix mechanism technique. In this case, we show that while the PELA's error estimations might be better for simple cases, it doesn't scale as well for more complex linear combinations. We will later show how to overcome this issue. Lastly, since the PELA's error estimations are theoretical upper bounds computed without executing the queries, we compare our results with empirical estimations of the errors. For a particular example of three-way marginal, We compute the theoretical error provided by our function accuracy, and we compare it with the empirical one obtained by executing the same program on a synthetic data, which is commonly used to work with high-dimensional datasets. Since computing the theoretical error will require to execute the query several times, while the Pella's estimations will only traverse the code once, we can see that the performance is many orders of magnitude in favor of the Pella, while the empirical and theoretical error remain well aligned. We also discussed the Pella's limitations and possible extensions. One of the Pella's biggest limitations is that it does not allow branching on noisy values to facilitate accuracy calculations. This restricts the type of analysis that can be implemented. To overcome this issue, we propose adding common differentially private analysis as black boxes. We show that this can be done as long as we have a way to compute their ICDF and the resulting value is considered to be tainted. This approach can also be used to support the matrix mechanism in the Pella as done in Apex. Lastly, there are several works exploring the use of post-processing techniques to boost the accuracy of the analysis. To this day, the Pella does not support this kind of optimizations since they rely on the notion of accuracy. To extend the Pella with other notions of accuracy, we will need to design their compositional theory. To sum up, we have introduced Dipela, a programming language for differentially private data analysis. It allows analysts to statically reason about privacy, accuracy, and their trade-off. Its key features are the implemented calculus to reason about accuracy via combinators and decomposition, together with the use of taint analysis to detect statistical independence and provide tighter error bounds. Also, it is an extensible tool. We have extended Dipela with other notions of differential privacy, such as epsilon delta dp, different sources of noise implementing Laplace and Gauss mechanism. We support other forms of composition, such as advanced composition, and we have added non-compositional primitive as black boxes. As an example, we have the noisy max. If you want to learn more about Dipela, we invite you to check our paper.